Greetings and welcome to the video for problem set number 2 of Chemistry 222, where we'll look at Chapter 8 and gases in detail. And I'm really glad to have you here. So like problem set number 1, I do recommend that you have a periodic table next to you. I recommend mhchem.org/per-tabs periodic table. I think that's a good one. It's one you'll use on quizzes and exams, so it's cool to get used to it. And like before, make sure that you mark every problem. Mark the problems that you got correct with some kind of mark so that I know what they are. And if you miss a problem, it's no big deal. Just cross out your old answer, put in the actual answer, maybe make some marks as to how you'll do it right next time. Should be pretty chill. You don't mark your problem set, you won't get full credit. You mark every problem, you will get full credit. So hopefully this is a pretty chill experience. If you have questions on this material, I definitely encourage you to talk to me. You can also talk to the AVID/LSC Center located above the MHCC library on the main campus. The website for that group is mhcc.edu/avid. The LSC offers free tutoring to you as a student at Mountain Community College, and they're pretty cool people, so I recommend that you check them out. It should be pretty cool. Okay, so let's see what this problem set has to offer. A sample of carbon dioxide gas has a pressure of 56.5 millimeters of mercury in a 125 milliliter flask. What is the volume of this gas sample when it has a pressure of 62.3 torr at the same temperature? So, welcome to the world of gases. Welcome to the world of math. All right, we're back into it after kind of being away from it in the Lewis structures, organic chemistry kind of section. And in the world of gases, you have to think about the different kinds of units here. And here we've got a couple of different kinds of units. We've got a millimeter of mercury and a torr. And those are both units of pressure, okay? And the milliliters right there, of course, that's going to be a unit of volume. So before we get into the problem, I just want to talk about the kind of units you're going to see. When it comes to pressures, there's lots of different kinds of pressure units, but the four that I really would like you to know are millimeter of mercury, torr, millibar, and atmosphere. And 1 atmosphere, which is the one we're going to use for most of the calculations, that equals 760 millimeters of mercury and 760 torr. So notice that a millimeter of mercury and a torr are the same thing. So when it says 62.3 torr up there, you can just rewrite that as 62.3 millimeters of mercury. The millibar will be important if you're taking a lab face-to-face with me. The type of pressure unit we record in lab is a millibar. There's 1,013 millibars per atmosphere, and that will be helpful when it comes to lab. Now, volume is something we have talked about, but we haven't talked about it for a while. So I think it's important to think about what's going on, talk about the units you might see. A milliliter and a centimeter cubed are definitely going to play a factor, but we're going to convert both of those into liters several times. So there's 1,000 milliliters in a liter, and there's also 1,000 centimeters cubed in a liter. What that means, if you remember from Chem 221, is that a milliliter is the same as a centimeter cube. Milliliters are usually used for liquids, or in this case gases. Centimeters cubed are usually used for solids, but a milliliter and a centimeter cubed are the same. So up there where it says 125 milliliter flask, you could call that 125 centimeter cube flask. It would be the same thing. So in this problem, we have pressure changing, we have a volume change, and we want to find out what the new volume is. As a quick reminder, though, before we look at the math, is that, wow, we're definitely back in the world of significant figures. And adding and subtracting sig figs will be important, as well as multiplying and dividing sig figs. So make sure you look back at Chapter 1, where we talked about significant figures. You can also, of course, let me know, and I'll try and help you out with this stuff as well. In this problem, the easiest way to do it is to use V2 equals P1 V1 divided by P2. And because the pressures there you can see are going to cancel out, P1 over P2, whatever those units are, if they're the same, they'll cancel out. The units of V1 will equal the units of V2. So in this problem, I wouldn't necessarily convert to atmospheres and liters unless you want to. What I just did is I used millimeters of mercury. Remember, 62.3 torr is the same as 62.3 millimeters of mercury. And you can see that the millimeters mercury on the top cancels millimeters mercury on the bottom. Milliliters is the only unit left out. 113 milliliters would be the answer. 113 milliliters would be 0.113 liters. And if you use liters, honestly, that's totally fine. Now, if this equation down here in the left is a little weird, what I do to remember all these different equations is I go back to the ideal gas law. And we're going to see the ideal gas law kind of dominates this chapter. The ideal gas law, which we will talk about more later, PV equals nRT. In this problem, the moles N, the R constant, of course, and the temperature are all constant. Only pressure and volume are changing. So what I do is I say, well, if I have an initial P1, V1, initial pressure and initial volume, that's going to equal some kind of final pressure and volume, i.e. P2, V2. And you can see then if you divide both sides by P2, V2 will equal P1, V1 over P2. This is how I remember all these different rules. This is Boyle's law, but you don't need to know that. You just need to know how to get to V2 equals P1 V1 over P2 to get the final answer. And then finally, again, back to the world of significant figures. This problem, you're multiplying and dividing. And so because all of the numbers have 3 significant figures, the number in your calculator, 113.362, etc., you want to cut that off at 3 sig figs. 113 milliliters would be the best answer. Define STP for gases. Then it says a 5 milliliter sample of methane gas at 1 atmosphere is enclosed in a gas-tight syringe at 22 degrees Celsius. If the syringe is immersed in an ice bath at STP, what is the new gas volume? Okay, so STP stands for standard temperature and pressure, and gases have their own standard temperature and pressure. And believe it or not, this is different from the thermodynamic standard temperature. We saw, for example, in Chem 221 that enthalpy, delta H, a lot of times has a superscript 0. That means standard conditions in thermodynamics. Well, unfortunately, or fortunately, depending on how you look at it, gases have their own STP. STP for gases is 1 atmosphere of pressure and 273 Kelvin. Okay, so STP for gases, 1 atmosphere, 273 Kelvin. In thermodynamics, 1 atmosphere is the standard pressure, but standard temperature, 298 Kelvin. And I don't know the history why gases standard temperature is different than thermodynamic standard temperature. Go figure. But anyway, just realize gases 273 Kelvin. So in this problem, we have a sample of methane gas. We want to know what the new volume is. And you can see here what's happening. It starts at 1 atmosphere and 22 degrees Celsius, and we're putting it in an ice bath. Now, ice has a temperature of 0 Celsius or 273 Kelvin. So when you look at all these changes that are going on, the pressure actually doesn't change. The pressure was 1 atmosphere to begin with, and at STP, it's 1 atmosphere as well. However, the temperature is changing. 22 degrees Celsius is certainly not 273 Kelvin, I'll tell you that. We'll talk about that in a little bit. And the volume is certainly changing. It starts at 5 milliliters and it ends up at some new volume. So this is a problem where really just temperature and volume are changing. When you want to convert from Celsius to Kelvin, and this is something we did in Chem 221 as well, you want to add 273.15 to the Celsius temperature to get Kelvin. Kelvin temperatures are super important, and you always want to use Kelvin when it comes to gas laws. Don't ever use Celsius. Celsius a lot of times is recorded in the lab, but then for calculations, you must use Kelvin. Celsius values can be 0 and negative numbers, which are all bad for calculations, so we must use Kelvin. In a lot of these problems, you'll go Celsius to Kelvin and you'll get an answer, and then sometimes you'll go back to Celsius. So just get ready. But remember, Celsius plus 273 equals Kelvin. Kelvin minus 273.15 is Celsius. So in this problem, 22 Celsius plus 273.15 equals 295 Kelvin. This is another sig fig thing. The 22 stops at the 1 spot, so 273.15 stops at the 100th spot. So our final answer here must stop at the 1 spot. When you add and subtract, the value always is going to stop at the largest doubtful digit. So in 22, the second 2 is at the 1 spot. 0.15 of the other number stops at the 100th spot. So you want to stop at the largest doubtful digit. 295 Kelvin would be the best answer here. This equation that you want to use, V2 equals T2 times V1 over T1. And I'll talk about in a little bit a way that you can get this from the ideal gas law. But remember, don't use Celsius, always use Kelvin for all temperatures. So you plug these values in. The final temperature was 273 Kelvin. You had 5 milliliters at 295 Kelvin. This comes out to be 4.6 milliliters, or 0.0046 liters if you did it in liters. To get this equation, remember that PV equals nRT, but only V and T are changing. So if you clean this up a little bit, you get V over T equals nR over P. And the nR and P values are not changing here. So what that means is V1 over T1 equals V2 over T2. And here we're solving for V2, so we'll multiply both sides by T2. That's where you get T2 times V1 over T1, figure out 4.6 milliliters, good to go. So again, make sure that always, in all your calculations in gases, you turn Celsius into Kelvin. That's going to be pretty important. A steel cylinder holds 1.50 grams of ethanol, and there's the formula for ethanol. What is the pressure of the ethanol vapor if the cylinder has a volume of 251 centimeters cubed and the temperature is 250 degrees Celsius? Assume all the ethanol is in the vapor phase at this temperature. So we're looking for the pressure. This is going to be a gas law question. And remember that the ideal gas law, PV equals nRT. But we've also got to get our units here in the right kind of piece before we start plugging it in. If you're going to use R, which we will in this problem, you have to make sure you have moles. So we're going to have to turn grams of ethanol to moles. We're going to have to turn volume to liters. We're going to have to turn temperature from Celsius to Kelvin, and we'll put this all together and see what the pressure is. So PV equals nRT. We're actually going to use it this time. R is a number you need to know / memorize / put in your calculators because we're going to use it a lot. There's different versions of R. This is what I'm going to call the gas R because it's with gases. Not just gases, by the way, we'll see that later, but for right now it's the gases. So this is the gas R, 0.082057. The units are liters atmospheres per mole Kelvin. That's why all of those have to be in the right kind of units. So the pressure we're going to calculate here is going to come out in atmospheres, but we must make sure our volume is in liters. So we're going to convert 251 centimeters cubed into liters. And remember, we'll divide that by 1,000 to get liters. We're going to have to turn the grams of ethanol into moles. So we're going to need the molar mass of the ethanol. We're going to have to add up all of those atoms from the periodic table and put them together to get the grams per mole. We can then take the grams, turn them into moles. Celsius, be good to go. And finally, we're also going to turn Celsius into Kelvin. So we're going to add 273.15 to the 250 to get the Kelvin temperature. Here's the molar mass, and I want to make sure everybody's clear on this too. So ethanol, C2H5OH. So if you add up 2 carbons, 5 hydrogens, an oxygen, and 1 more hydrogen on the periodic table, that comes out to be 46.07 grams per mole. So grams divided by grams per mole, you get the value of moles right there. That's the number we're going to use in the ideal gas law. The volume, remember that a centimeter cubed is the same as a milliliter, and there's 1,000 or 10 to the third milliliters per liter. So this comes out to be 0.251 liters. And 250 Celsius, if you add 273.15 to it, initially you get 523.15 Kelvin. I'm going to come back to that here in a little bit though, so hang on. Anyway, now I've got Kelvin, liters, moles, I've got R, so the only thing I don't have now is pressure. Let's put all of those numbers in. Now, in your calculator, you're going to get 5.568538, etc., etc. And the question is here, how many sig figs? And you'll notice up here, I was kind of cheesy with the temperature. 250, the 250 number, officially the 250 stops at the 10 spot. In the chemistry world, 250 dot would be a 3 sig fig number, and 250 without the dot would be a 2 sig fig number. 250 with the dot means that the plus or minus, the uncertainty, is at the 1 spot. So at 250 dot, you'd say the number was between 249 and 251 in my experimentally obsessed science. 250 without a dot would be plus or minus 10. So 250 without a dot, you'd say 240 to 260, something like that. You have a greater uncertainty in the 250 without a dot than you do with the dot. So if you don't see that dot by the 0, that means the 0 does not count. And 250, it literally, that has a 2 sig fig number. So over here at 523.15, officially, you would cut it off right there. It would be like 520. But you don't want to use 520 in the answer. You want to use the whole 523.15. But because the temperature should have been a 2 sig fig number, that's why the very best answer here, 5.6 atmospheres. That temperature is enough to kind of mess up everything. Even though it looks like it should be 3 sig figs, it's technically 2 sig figs, 5.6. So anyway, these are just things to remember. These are things we talked about in Chem 221, and they're coming back to us here big time. As you can see in the ideal gas law, you have a lot of multiplication, division, but you also have adding and subtracting when it comes to temperature. So just realize there's a lot of things to think about, but it's all stuff you can do. Diethyl ether vaporizes easily at room temperature if the vapor exerts a pressure of 311 millibars in a flask at 25 degrees Celsius. What is the density of the vapor? Okay, so densities of vapors, densities of gases are an important topic in this area. And as we talked about in lecture, you can take the PV equals nRT and transform it into what I called the evening dirt equation. PM equals DRT. And PM equals DRT is cool for us because it does relate the density, which is what we're trying to solve for here. It relates the density to the molar mass M. And so in this equation, the evening dirt equation, R is again the gas constant R, P is the pressure in atmospheres, and big M there, that's the molar mass in grams per mole. Density is the density of the vapor in grams per liter, and T is the Kelvin temperature. So if you look at all these values right here, all right, the 311 millibar is a pressure. We're going to translate that into atmospheres using that 1013 millibars per atmosphere conversion I talked about earlier. Woohoo! 25 Celsius we'll have to turn into Kelvin, and M, the molar mass, we're going to find the molar mass of the diethyl ether. So let's do the millibars first. 311 millibars, you can turn that into atmospheres by dividing by 1013. 0.307 atmospheres, 3 sig figs in, 3 sig figs out. 25 Celsius becomes 298.15. Now again, thinking of sig figs, when we do this, 25 cuts off at the 1 spot. So officially this would cut off at the 1 spot as well. But I do encourage you to use 0.15. Use all the sig figs you can, and at the end, go back and do the sig fig analysis. So the density, if you solve for D, equals PM over RT. And again, the M is the molar mass. So if you add up the 2 ethyls and the oxygen, it comes out to be 74.12 grams per mole. Again, use the periodic table to do this. But if you did it right, you'll get a molar mass of 74.12. The pressure, 0.307 atmospheres times the molar mass divided by R divided by 298.15. Basically everything in this problem, it more or less is 3 sig figs. Well, that's not really right. The molar mass was here 4 and R was 5, but pressure and temperature, like we talked about earlier, are 3. So 0.930 grams per liter would be the best answer here. Chloroform is a common liquid used in the laboratory. Vaporizes readily, i.e. we're going to think about it as gas. Anyway, if the pressure of the chloroform vapor in a flask at 195 millimeters of mercury at 25 degrees Celsius and the density of the vapor is 1.25 grams per liter, what's the molar mass of the chloroform? So we can actually use the gas laws to solve for the molar mass. If your gas problem has a density in it, which this one does, I do recommend once again using PM equals DRT. Now we've got to get all the units in the right piece. So 195 millimeters of mercury divided by 760 gives you 0.257 atmospheres. We've got to turn our Celsius into Kelvin. But if PM equals DRT, then M, the molar mass, equals DRT over P. Now density is already in grams per liter. We don't have to do anything there. We do have to turn the Celsius into Kelvin. We've got the pressure. We know R, plug and chug, 1.25 grams per liter times the R constant, 0.082057, times 298.15 Kelvin, divided by the pressure, 0.257 atmospheres, 119 grams per mole. And again, 3 sig figs from both the pressure and the density. So let's call it at 3 sig figs. The temperature here would technically be 4 sig figs, 25.0. You would round the 298.15 to the 10ths place. Again, that's because this value has a 10th, but that's not a big deal because, again, 3 sig figs is limited here by our density and pressure. Oh, chemistry. A 0.0125 gram of sample of a gas with an empirical formula CHF2 is placed in a 165 milliliter flask. It has a pressure of 13.7 millimeters of mercury at 22.5 degrees Celsius. What is the molecular formula for this compound? Okay, so this is a question that we kind of looked at in Chem 221, where we're taking an empirical formula and turning it into a molecular formula. But in Chem 221, I would give you the empirical formula and the molar mass, and from that you could find the molecular formula. In this problem, we're first going to solve for the molar mass, or we're going to use that M equals DRT over P thing again, and that's going to allow us then to find the molar mass. You could also use the ideal gas law. You could solve for moles N first, and then grams over moles N would give you the molar mass, and either way is totally fine. Once we have the molar mass, we will also find the molar mass of the empirical formula unit. We'll compare the molar mass of everything to the molar mass of the empirical formula. It should give us a whole number. So the answer here, the molecular formula, will be that CHF2 taken N times. So the answer here could be just CHF2. It could be CHF2 taken twice, which would be C2H2F4. It could also be C3H3F6, etc., etc. So let's do this. First of all, we have to find the molar mass, and there's different ways to do it. You could use PM equals DRT. You could also solve for moles first and equals PV over RT, and then grams per mole, and it really doesn't matter which way you do it. In this problem, I decided to try and do it the molar mass from PM equals DRT. Now, density is mass over volume, grams over liters, so I got the value there, 0.075 grams per liter. Got to turn millimeters of mercury into atmosphere by dividing by 760. And of course, yes, you must convert Celsius to Kelvin. I used 273.2, which is the value to the 10th of 273.15, round the 1 up to 2. Anyway, plug all of this stuff in to find the molar mass M. And molar mass M is, again, dRT over P. You can see all the different values there, which we have. The density is limiting us to 3 sig figs, as well as the pressure. So the 101.955, et cetera, that's 102 grams per mole. That would be 3 sig figs. Now, this is the molar mass of the whole thing. And what we need to do now is find the molar mass of that empirical formula piece. So if you add up a carbon, a hydrogen, and 2 fluorines, that comes out to be 51 grams per mole. If you look on the periodic table, carbon is about 12, hydrogen is about 1, and fluorine is about 19. So 19 times 2, 38, plus carbon is 12, that's about 50, plus hydrogen about 1, 51 grams per mole is the empirical formula of CHF2. And we'll compare that to the molar mass of the whole thing. If 102 on the top, 51 on the bottom, you're always going to get a whole number, no fractions. The fraction here, the whole number is 2. So that means the molecular formula will be twice the empirical formula. So notice that this 2 right here is what we used right there. It says how many empirical formula units are in the molecular formula. So because we're taking it twice, molecular formula C2H2F4. Cool. We're going to do this problem again in a little bit, but in a problem where we don't have the empirical formula. So this process will be helpful to us later on. Silane, which is SiH4, reacts with oxygen to give silicon dioxide and water according to the equation shown below. A 5.20 liter sample of silane gas at 356 millimeters of mercury and 25 degrees Celsius is allowed to react with oxygen gas. So it's saying what volume of oxygen gas in liters is required for the complete reaction if the oxygen has a pressure of 425 millimeters of mercury at 25 degrees Celsius. And there's the overall reaction. Okay, this problem, there's several ways you can do it, but the way that I'm going to push you towards is we're going to use good old stoichiometry. That means that 1 mole of SiH4 needs 2 moles of O2. If you dig through this problem, you've got a volume of silane, a pressure of silane, and a temperature of silane. So in the first part of this problem, we're going to find the moles N of SiH4, and that's going to be PV over RT. So the first part of this problem, let's solve for the moles of silane, PV over RT. Cool. In the second part of this problem, we're going to take the moles of silane and multiply by a 2-to-1 ratio, because 2 moles of O2 are needed for every 1 mole of SiH4. So in step 2, we're going to turn our moles of SiH4 in step 1 into moles of I2. In the final step, step 3, we want to find the volume of oxygen gas. Volume by the ideal gas law, nRT over P. And we've got the pressure, we have the temperature. We're going to calculate the moles in step 2, so the only thing then we don't have will be the volume. So let's look at the math for this one. So again, first find the moles of silane, that's step 1. Convert to moles of oxygen, that's step 2. And then finally, step 3, find the volume of the oxygen. So moles of silane, N equals PV over RT. So here's the atmosphere's pressure for the moles of silane. The volume of silane is given. R, 25 Celsius is 298 Kelvin. That comes out to be to 3 sig figs, 0.0996 moles of silane. So that's the answer to step I up there. Now the second part then is we're going to convert moles of silane into moles of oxygen. We need a 2-to-1 ratio. And again, this ratio right here came from the balanced equation. 2 moles of O2 for every 1 mole silane. That's 0.199 moles of O2. And then finally, the last step, we're going to solve for the volume of O2. V equals nRT over P. And make sure, of course, you use the oxygen numbers in the volume of oxygen calculation. Make sure you use the silane stuff in the moles of silane calculation. But if you do all of this, nRT over P, again, we're plugging the moles of O2 in, RT over P, 8.71 liters. So this is the way that I recommend that you do this problem. You can sometimes get by other ways. For example, the temperature is 298 Kelvin in both ways. R, of course, is the same. So you can do it some other tricky ways, but I find that it's tricky for students. Sometimes they forget the 2-to-1 ratio or something like that. So this is the way I encourage you to do it. But if you do it another way and you get the same answer, hey, I'm not complaining, that's for sure. So good. Equal masses of gaseous nitrogen and argon are placed in separate flasks of equal volume at the same temperature. Tell whether each of the statements is true or false and briefly explain your answer. I want to talk about a little bit what equal masses means for this problem. Now, in the ideal gas law, which we've seen a lot, PV equals nRT. So moles are kind of the ingredient that we need to think about when it comes to gases, not masses. Okay, and you'll see why here in a little bit. So what you can do on a problem like this is just pick a number, and they can be any number you want, but whatever number you pick, it's going to be the same number of grams for N2 and the same number of grams for argon. So let me pick just a number somewhat at random. Not really, but anyway, somewhat at random. Let's pick 28 grams. So we're going to say if they're equal masses of N2 and argon, that would be 28 grams of nitrogen, and that would also be 28 grams of argon. So equal masses means equal grams. Now, what I'm going to do works regardless of what number you pick, but you'll see why I'm picking 28 here in a little bit. So, because moles is the ingredient, one of the ingredients in the ideal gas law, we must turn these numbers into moles. Now, nitrogen, a mole of N2, is about 28 grams. So 28 divided by 28, that's 1 mole of nitrogen, okay? 28 grams of argon, though. Argon on the periodic table, if you look at it there, number 18, 39.948. So I'm using such cheesy sig figs, I'm going to use 40 grams, 39.948, whatever, 40 grams, okay? What we're going to see here is you're going to get less than 1 mole of argon. 28 divided by 40, all right, is definitely a number that's less than 1 mole, okay? So notice here that if they're equal masses, because of the differences in molar mass, you're going to have more moles of N2 than you have moles of argon. And again, you can pick any number you want. You can pick 0.000001 grams. You can pick a billion grams. You're going to see that there's more moles of N2 than there are moles of argon, and you can try it yourself. Now that we've got the moles out of the way, here's a few helpful hints. So you can see number one, molar mass of argon is greater than the molar mass of N2. And so samples with equal mass, and I picked 28 grams, but you can pick any number you want, you're going to find more moles of N2. And because moles are proportional to molecules or atoms, you're going to have more molecules of N2 than you're going to have atoms of argon. I'm also going to throw this equation in there. It's the energy of a gas. We'll talk about this part in a little bit, so just hold that thought for a second. But let's look at answer A. It says there are more molecules of N2 present than atoms of argon. True. If there are more moles of N2 than there are moles of argon, then that means if you multiply both of those numbers by Avogadro's, there's going to be more molecules of N2 than there are atoms of argon. So the first one is definitely true. The second one, the pressure is greater in the argon flask. Well, remember here that pressure, PV equals nRT. Guess what? P and N proportional to each other once again. So the higher moles will have the higher pressure, and the higher moles is not argon, the higher moles is nitrogen. So B is going to be false. There's more pressure in the N2 part because nitrogen, there's more moles, there's more molecules, and molecules, as you see, are kind of proportional to pressure here. So B is definitely false. There's going to be less pressure in the argon flask. C says the argon atoms have a greater average speed than the N2 molecules. And let's focus again on the energy equals 3/2 kT equals 1/2 mv squared. All right, if you have two samples of gas at the same temperature, and that's what the T part is right there, then they're going to have the same energy. Temperature is proportional to energy. K is called the Boltzmann constant. It's nothing you need to know, but it is just a number you can look up. It doesn't change. So if you have gases at the same temperature, they're going to have the same energy. All right? So in this example, both argon and nitrogen are at the same temperature. They're going to have the same energy. But this question wants to know about speed. And in science, V is the symbol for velocity, which is usually meters per second. That's the speed, if you will, of these molecules. So notice that if the energy is the same for both of them, energy also equals 1/2 mv squared. Okay? Now, m is the mass. And for molecules like this, you can think about the molar mass that we used earlier as being a way to tell what the mass is. So if you're looking for the biggest speed, all right, and the energy is the same, you're going to have the smallest mass. Now this is kind of weird. You're at the same temperature, so both nitrogen and argon have the same energy. Energy equals 1/2 mv squared. The energy is the same, but their masses are certainly different. Like nitrogen is a smaller mass and argon is a bigger mass. So if you have a bigger mass and the energy is the same, your speed V is going to be smaller. On the other hand, if you have a smaller mass m, then your V is going to be bigger because m times V squared times 1/2 is always equal to the mass. It's going to be the same thing. So C is false, all right? Heavier atoms move slower than smaller atoms. And I'm using the molar mass here to tell which one is bigger and smaller. Nitrogen is smaller, 28 grams per mole, relative to bigger argon, 40 grams per mole. If nitrogen and argon were on a track, running a race, all right, nitrogen has less mass, it would probably go faster. Argon has more mass, it would probably go slower. So all of this comes out in this weird E equals 3/2 kT equals 1/2 mv squared. All gases have the same energy if they're at the same temperature, but if the energy is the same, then you have to think about mass and speed velocity, and as one goes up, the other one goes down. Use the molar mass to see what the mass is. D, the N2 molecules collide more frequently with the walls of the flask than do the argon atoms. I kind of covered up the atoms part there. Sorry about that. This part here has to do with number of molecules, because if it collides with the walls of the flask, that's the pressure. That's another term for saying pressure. And we already saw that higher pressure comes from higher moles, which is N2. So because we have more molecules of N2, they're more likely to run into the walls of the flask than the argon, because there's just less molecules there. So true, the last one's true. Nitrogen molecules have a greater velocity, all right? They're smaller, so they go faster, and there's more molecules of them, so they collide more frequently. The flask doesn't have a chance. This is a great question because it really, I think, kind of nails the coffin on some of these kinetic molecular theory ideas when it comes to gases. And you can see the ideas. If you have more moles, you're going to have more pressure, but bigger molar masses go slower. Their velocity is less if the mass is greater, and vice versa. Pretty cool. For the last part of this problem, it says the argon will diffuse faster than the N2. And big surprise, this comes down to molar mass once again. Argon is just a bigger molar mass, and things that are bigger go slower. Things that are lighter go faster. So E is false. Argon will not diffuse faster because it's bigger than N2. Argon will diffuse slower. N2 is lighter. It's going to be a little bit faster going through things than argon will be. So again, hopefully this problem will give you an overview as to the important things about how molar mass affects the kinetic molecular theory, diffusion, effusion, speeds, all this kind of jazz. And again, if you have any questions, let me know. We've got a gaseous chlorofluorocarbon, a CFC for short. And so that means it has carbon, chlorine, and fluorine. And when they analyze this CFC, it has 11.79% carbon, 69.57% chlorine. You'll notice it doesn't have fluorine, but if fluorine is the only game in town, then 100% minus those two numbers will give you the percent of fluoride. We find in another experiment, this is a separate experiment, that 0.107 grams of the compound fills a 458 milliliter flask at 25 degrees Celsius with a pressure of 21.3 millimeters of mercury. What is the molecular formula of this compound? All right, quick check here as to what's going on. In Chem 221, one of the big things we did was we took raw data and we turned it into an empirical formula. And from the empirical formula and the molar mass, we found the molecular formula. And at the time I said, oh yeah, the molar mass value is like a black box, something like that. Well, using our understanding of how gases work, we can actually calculate the molar mass of the gas itself. So let's say again, someone hands you a brand new compound, right? You don't want to just drink it or something like that because probably it's toxic or at very least not good for you. What you want to do normally is have like a two-step analysis. And one of the steps is literally to find the mass percentages. And from the mass percentages in Chem 221, we could turn those into empirical formulas. But then you need a second experiment to give you the molar mass. Well, our second experiment is a gas law, all right? We've got this much mass, this much volume, it's this temperature, and this pressure. And that's all we need in order to find the molar mass of the gas. So if we have the empirical formula and the molar mass, we can use that to define the desired molecular formula, the holy grail sometimes of chemistry and stuff, which is cool. So in this problem, we're first going to find the empirical formula based on the percentages. This is a review from Chem 221, and if you don't remember this, by all means, feel free to look back in Chapter 2, Part 2 of my lecture notes from Chem 221. There were some examples of this process, and it's not hard or anything like that. Anyway, once we have the empirical formula, we'll use the gas law pieces to find the molar mass, and from the empirical formula and the molar mass, we'll be able to find the molecular formula. Okay, let's get started. So again, here's kind of the idea. Number one, find the empirical formula, the EF, from the percent elements. Then we're going to find the molar mass from the ideal gas law using all those gas pieces. And finally, we'll find the molecular formula using the empirical formula and the molar mass. So kind of a three-step process. Okay, so in step one, to find the empirical formula, first we have to find percent fluoride, okay? So 100% minus the other two percentages will give you the percent fluoride, 18.64%. No problem. In Chem 221, what I told you to do was to assume you have 100 grams of compound. So if you have 100 grams of compound, for example, then you'd have 18.64 grams of fluoride. And once you have the grams of element, you can use the molar mass of the elements to turn grams into moles. And that's exactly what I did right here. So 11.79% carbon became 11.79 grams of carbon. And I looked on my periodic table, 12.011 grams per mole, so I got 0.9816 moles of carbon. And we did the same thing with the chlorine, 35.453 again comes from the periodic table, and the fluorine, there's the molar mass of fluorine. So here are my 3 mole values, assuming 100 grams, which is awesome. And this is actually enough to make a very rough formula. Like you could write it as C.9816, Cl 1.962, F 0.9812. But that's a pretty ugly formula, right? Most of the time things are CO2 or NaCl, right? They're whole numbers, okay? So to get whole numbers, you want to divide all of those 3 numbers by the smallest number of moles, which is 0.9812. So if you do that, notice how here's 0.9812, the smallest. I put the carbon on the top, and that's almost exactly 1-to-1. On the other hand, 1.962 divided by 0.9812, that's more like a 2-to-1 ratio. So you can see here that for every 1 F, we have 1 carbon, and for every 1 F, we have 2 chlorines. So you put this together, 1 C, 2 Cl's F, empirical formula CCl2F. Score. Now, this is the smallest whole number ratio of atoms. This is not the final answer, okay? The empirical formula is just a step in the right direction. Now what we're going to do is find the molar mass of the gas, and from that then we can use this empirical formula to go to the molecular formula. So in step 2, you can say we've got the empirical formula, that's down. We found it with CCl2. Now, later on, we're going to need the molar mass of CCl2F. And so if you add up a carbon and 2 chlorines and an F, it's 102 grams per mole. And we'll come back to that in a little bit. But what we need first, though, is the molar mass of this gas. And we'll use the ideal gas law to do it. So remembering that PV equals nRT, you can actually rearrange this in different ways. I'm actually here using molar mass equals dRT over P. That's PM equals dRT, but solve for M. Now the density is going to be the grams over volume. Grams over volume in liters would be the density. We'll use good old R, 0.082057, the temperature in Kelvin, and in the bottom we'll have the pressure in atmospheres. Now before I show you the math, I want you to know this isn't the only way to do this problem. You could also solve for N, the moles, N equals PV over RT, and then the molar mass would be the grams, 0.107, divided by the moles, and that would be fine. There's even another way. If you did the lab with me in person in the volatile liquid lab, sometimes I use an equation where M equals GRT over PV. That's another way to solve for molar mass. All of these ways are fine. So if you did it differently than me but got the same answer, I have no problems with it whatsoever. Here's the way I did it using dRT over P. So again, D is going to be mass over volume, and I turned the volume to liters because gases are always grams per liter. There's R, 0.082057, T, Kelvin temperature, and in the bottom, I turned 21.3 millimeters of mercury into atmospheres. So if you did it right, and again, you don't have to do it this way. If you did it another way, that's fine, as long as you get 204 grams per mole. That's the molar mass of the entire molecule, the entire thing here, the CFC. The last step, we found the molar mass, that's 204 grams per mole. The last step is to compare the molar mass of the whole thing to the molar mass of the empirical formula, that 102. This ratio will always be a whole number, 1, 2, 3, something like that. You won't have fractions or anything strange. So you can see here that in this case, 204 divided by 102, and again, 204 is the molar mass of the whole thing, and 102 is the molar mass of the empirical formula. It's obviously a ratio of 2. So that tells us that we need 2 empirical formulas in our molecular formula. So we're going to take the empirical formula, CCl2F, and multiply it by 2, the molecular formula C2Cl4F2. Yeah. I say yeah because in chemistry this is kind of a cool thing. To find the molecular formula of a compound is a pretty kind of groovy thing for chemists to do. And it's kind of a cool rush to go through all this stuff and see what's happening. They're very straightforward. Make sure your units are in the right kind before you use them in the ideal gas law. You don't have to use M equals dRT over P. Like I said, there's other ways to do it. And if you did it a different way, that's fine. Cool. You're given 1.56 grams of a mixture of potassium chlorate, KClO3, and potassium chloride, KCl. When heated, the KClO3 decomposes to KCl and O2 according to that reaction shown. Then it says we have 1.56 grams of a mixture, and it creates all this information of oxygen. And it's all about oxygen because in the equation you can see oxygen is a gas. We can use this information to calculate the weight percent of potassium chlorate in the mixture. Now in this problem, we're going to actually solve for the moles of O2 because moles N equals PV over RT. And so if we put all of those units in the right kind of values, we can then solve for moles of oxygen. We'll use a 2/3 ratio to convert moles of O2 to moles of KClO3. And finally, we'll multiply that by the molar mass of KClO3 to get the grams of the good stuff, the grams of the pure KClO3. And it had better be a number less than 1.56 grams because that 1.56 grams, that represents an impure mixture. It's a mixture of the good KClO3 and some impure KCl. So at the end of the day, grams of the pure KClO3 divided by 1.56 times 100%, that's going to give us the weight percent. But first, let's go back. Let's find moles of O2 because this is a gas, all right? So first we're going to find moles of O2 from the ideal gas law, N equals PV over RT. We can then use the 2/3 ratio to turn moles of O2 into moles of KClO3 and then into grams of KClO3 using the molar mass. And then finally, whatever number that is, divided by 1.56 times 100, that's going to be the mass percent. Here's the moles, N moles of O2. I turned the 735 millimeters of mercury into atmospheres. I multiplied by the liters of gas that it was taken up. So you can see milliliters to liters, stuff like that. Here's the gas constant R. Here's the Kelvin temperature. Again, never use anything but Kelvin in these equations. You get 0.0132 moles of O2. There's the exact number, but I rounded up to 3 sig figs because of the volume, etc., etc. By the way, the temperature, 19 degrees plus 273, makes it a 3 sig fig 292. When you add and subtract, it's all about where the doubtful digit is. 19 stops at the 1 spot. So when you add 273, you also want to stop at the 1 spot. Your 2 sig fig temperature was turned into 3 sig figs in the equation. That's why it's legit to use 3 sig figs for the moles of O2. Next part, we found the moles of O2. Next part, we're going to take moles of O2 and turn them into moles of KClO3 and then grams of KClO3. This 2/3 ratio comes from the fact that there are 3 moles of O2 for every 2 moles of KClO3. This is good old stoichiometry from Chem 221. And once you have moles of KClO3, you can use the molar mass of KClO3, the 122.5 number, to turn moles of KClO3 into grams. 1.08 grams KClO3 in the mixture. And again, that's the grams of the good stuff. But there was a total of 1.56 grams total. So if you're curious how much, what the percentage, I guess I should say, of the good KClO3 is, 1.08 divided by 1.56 times 100%, this mixture is 69.1% KClO3. Because KClO3 breaks down a little bit over time, this process is actually used. If you know how pure your KClO3 is, you can add a little extra and still have the same result if you use pure KClO3. So, woohoo, go science. Okay, so that's it for problem set number 2 of Chemistry 222, and I appreciate you spending your time with me. If you have questions on any of this material, I do encourage you to reach out to me, the Avid Center /LSC Center located above the library on the main MHCC campus. And in addition, there's also study guides to help out. In the companion and online, there are study guides and concept guides to help you through the material. There's also the online-only chapter guides, which can help you to see some of the assets available to help you learn this material. Thank you for spending your time with me. I really do appreciate it, and I hope this has been helpful. Good luck with your studying, and have a wonderful day.